All right, so on to 8.2. So 8.2, one thing we kind of already discussed was this right here. Oops. So a nth root means n is the index and x is the radicand. Now also the key idea of 8.2 is that it turns out we can complicate this a little bit. Who would have thought that in math you can make things more complex? That you can, essentially have an nth root of something inside of some funky power. And it turns out that what you're allowed to do is write that in a few different ways. Well, number one, if you want, you can actually switch that up. Gotta switch when I'm copying. There you go. You can switch that up to actually kind of switch the order there. You could have the m raising the power of the entire root, or you could have the root being wrapped over x to the m. So that's kind of interesting that the exponent of m can either be outside of the root entirely or inside the root, and the expression is equivalent. The crazier idea is that, well, you can actually write that as just a fraction where the exponent, so to speak, so m is the exponent here, and m is the exponent here, becomes a numerator, and the root, or the index, becomes the denominator. So that is the big idea of 8.2, is that a root can be written as a fraction. And why does that make sense? Well, let's look at some roots you've seen before. We call it square root, cube root, but after that, if you notice, we sometimes refer to them as like fourth roots. Well, think in your mathematical vocab, where do you hear the word fourth? Well, typically you would hear it like this, like I need a fourth cup of, I don't know, sugar in my cookie recipe, something like that. A fourth is a fraction, so a fourth root is the fraction for 2x as an exponent. So in other words, a fourth root looks like x to the 1/4, 1/4 in the exponent. That's the idea going on here. Again, to fully iterate that idea is, well, that x there doesn't have a power, and if you don't see an exponent, the implied exponent is 1. So there is an invisible 1 there, that's why I get 1/4. So that's a very interesting result right there. And that result actually might simplify some things before. If we scroll back up and look at 8.1, maybe that illuminates what's going on here, because when you have a square root of x to the 12th, why is that 6? Well, because 12 divided by 2, right, this rule, a square root has an invisible 2 out front. So if you had a 12 on top and you had a 2 root, well, 12 over 2 is 6. Same idea, 18 over 6 is 3. And finally, 3 over 3 is 1, those exponent 3 and that root 3. So that's the idea going on there, and that's why if you kind of, in the back of your mind, are thinking, it feels like I'm just dividing these things, well, you were, and this is why. If you have an exponent on the inside and a root on the outside, those two are dividing each other. So anyways, well, what would the radicand be? Well, the radicand is the stuff on the inside of the root, so in other words, in this fractional exponent land, the radicand would simply be the 7, the thing that has the fractional exponent, or the rational exponent. Say the root index, so what they mean by the root index is, well, yeah, what is the thing that would be on the outside of that root? Well, the denominator would be that thing, so 7. So the 3 is just acting as a normal exponent. All right, let's see here. If we have this with n equals even, and this is in lowest terms, what restriction would be placed on a? Well, if I was evenly rooting something, no matter what that m is, well then the value of a would need to be non-negative, because again, I cannot evenly root any negative number. All right. If n were odd, well, if you try to odd root, there are no restrictions, because you can have a positive or negative on the inside of an odd root. And we saw that in 8.1. You can cube root -8. You can cube root positive 8. Cube roots, fifth roots, seventh roots, any odd root is fine with positives or negatives. So this homework can kind of be frustrating the first time you do it, because first it just says rewrite using radicals. So the first thing they want you to do is just realize that that's the same as the square root of 16. Then they want you to answer. So the answer would be 4. All right. Up next, this is kind of tricky, because maybe you're thinking that you can't square root negatives, but this is a very subtle exponent rule. It turns out that that negative out front is not actually, let me simplify what I'm copying here. That negative is actually not a part of that exponent. If it was, they would have to write it like this. All right, they would have to write it like that if they wanted the negative to be included. Now, if the negative was included, then the answer would be no solution, because I can't evenly root a negative number. But because that negative isn't in parentheses, since it just looks like this, the idea is what they're actually asking you to find is this, the negative square root of 64. The negative is not a part of that exponent. So negative square root 64. Now, if you have a scientific calculator and you type that in, you'll see that it won't say no solution. It will end up saying negative 8, because there is a negative in 64 roots to 8. Now again, if that were wrapped entirely in parentheses, then your calculator would spit out no solution. So up next, rewrite this expression with radicals. Well, that's a 3 root of z to the first power. And, well, that actually doesn't simplify really necessarily, so I guess I'm going to say it can't really simplify. There's nothing really to do with that. There's no way I can rewrite it. All right, so same idea, rewrite. Well, that 6, again, that 6 isn't in parentheses, so that exponent actually isn't applying to 6th, it's only applying to r, so that's the 5th root of r to the first power. And once again, that can't be simplified. There's nothing to do beyond that. All right, now 16 to the 5/4. Let's see what that can be. That could be, well, the 4th root of 16 to the 5th. And they want to see if I can simplify that. And the thing is, you actually can simplify that. And let's see, well, I'll leave that there, which is negative 8. Okay, so other ideas here. Let's look at this one. So if I've got the 4th root of 16 to the 5th power, what I think I'm going to do for this example is I'm going to use the rule that says I can essentially switch the order of that. In other words, I want to look at it like this. The reason I want to do that is because, well, 16 to the 5th power is really, really huge, and I don't necessarily know what that is off the top of my head without the use of a calculator. Now, you might not know what the 4th root of 16 is without a calculator either, but the idea is you can 4th root 16. It turns out if you do 4th root 16, you end up with 2. And then 2 to the 5th power is simply 32. So it can be simplified. That whole thing just ends up being 32. All right, now that's a big idea there, that you can make things smaller before you make them bigger. You can root something before you raise something. Now, of course, you can actually raise 16 to the 5th power and then take the 4th root in your calculator. It will still spit out 32, but you're going to get a very huge number after you 5th 16. You know, depending on your mental math ability, you might actually know what the 4th root of 16 is offhand, and then you could raise it to the 5th power. All right. Now also, one thing just to say, since we are delving into some wild roots here, really the only way to get good at working with roots and exponents is really just by kind of listing them out. You know, like 2 to the 1st is simply 2, 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16. If you notice, all you're doing there is just multiplying another 2 to your last answer. So you can kind of start to grid those out and write that nicely for yourself, like, you know, writing that again, you know, 2 to the 1st is 2, and then underneath that, 2 squared, this is not fun to type, 2 squared is 4, and you do that for, maybe the first 6 powers of 2, just to have them written down, and then you can go through the same process with 3. 3 to the 1st is 3, 3 squared is 9, 3 cubed is whatever, 27, and so on and so forth. And maybe if you write down the first few initial powers, eventually you might start to recognize some of those as they show up in Chapter 8. Anyways, let's move on. This time there is a negative in my root, but that's okay because I am oddly rooting that negative expression. First, how do I rewrite that using exponents? Well, that cube root is what goes there, and I still need to wrap that entire thing in parentheses, which will look like that. All right, now again, even though I wrote it like that, where the squared's on the inside, what I'm going to do to solve that is I'm going to, let me grab this. That looks most like what we last did. I'm going to rewrite it in this format so that I've got the cube root of negative 27, and I want to square that. Well, the idea is, again, the cube root of negative 27 is negative 3, and then they want me to square that, which is going to end up being positive 9, because when I evenly root a negative number, it will become positive. Again, if you just slam that all into your calculator as is, there is a way to, on a scientific calculator, even write that as a fractional exponent. You can type that all in one step and just get 9. You don't need to show all this work, but I'm trying to show you why all of this is true. All right. Up next, rewrite the expression using radicals. So this idea happens a lot. This is our first fractional idea, though. Now that is a square root, so I don't need that special extra number. But I do need to, maybe I can even write it like this also. I put the exponent on the outside. Will it accept that? It does. So you can switch the order there. You can either put 1/4 all to the 7th on the inside with a square root, or you can do the other way around. So again, the reason I'm doing it this way is because this is kind of how I mentally solve this, because if I want to square root 1/4, well, that simply comes down to, well, what is the square root of 1? Well, the square root of 1 is 1. What's the square root of 4? 2. But I still have to raise that to the 7th power, and I can't write it like that. I need to just write my final answer. Well, 1 to the 7th power is just 1, and 2 to the 7th power, I'm not quite sure, let me use a calculator, is evidently 128. So again, definitely your calculator is going to come in handy in this section. Rewrite this expression using radicals. All right, 6 to a plus 6 all to the 5th power. And there's definitely no simplifying that. Just trust me. And what number is used as the denominator of the exponent? Well, that's the index. We've already talked about that before. The denominator is the index. All right, so now we have the root. Rewrite it as a rational exponent. Well, 18 is to the 1st power, so 1/7. All right, and this would be n to the 3/7. I think at this point, if they all look similar, I might just skip over the next few. Well, this is interesting. This would be 4 to the 5/6 in the denominator. And in case you forgot, if you've got a exponent in the denominator, you are allowed to rewrite that into the numerator so long as you negate the entire exponent. So again, that was 4 to the 5/6 in the denominator, which I can move to the numerator as long as I negate the exponent. All right, up next, same idea. 3x is just going to tag along there. That's z to the 4/5 in the denominator. So if I want to write that in the numerator, I need to negate that exponent. And I'm going to skip over that. I think you can do it. And we've got one last question using our laws of exponents here. So the idea here is we got a to the 14/3 times a to the 5/6, and they want me to perform this operation. Well, the idea is when you are multiplying bases that are the same, what you're allowed to do, is you're allowed to simply add those exponents. And we've kind of seen that before, so that means I've just got 14/3 plus 5/6 in the exponent. Well, the problem with that is that you can't add fractions that don't have the same denominator, so I need to find common denominators. Well, 3 and 6 share 6, or that's the least common multiple between both of them. So I simply need to multiply 14/3 by 2/2. If I do that, I'm going to get 28/6. Right? So again, 28 is just 14 times 2. 6 is just 3 times 2. So all I did was I multiplied this by 2/2. I didn't change its value, I just changed how it looks. But now I have a common denominator, so I can add my numerators. So 28 and 5 make 33, and I can put that over the common 6, which, by the way, that does reduce just a little bit. That would be a to the 33, and 6 have 3 in common, so 11/3. A to the 11/3, and they want my answer with exponents and rational exponents. Whoops. What have I done? There's a mistake somewhere. Where is it? Type exponential notation with rational exponents. 1 minute. 28 and 6. 28 and 5 is 33. Oh, sorry. Yeah, that's what it is. 6 has a 3 in it, which will divide to 2. My bad. There we go. All right, and that does it for 8.2.